We are now going to start Unit 2, and Unit 2 is all about polynomial functions. We've already talked about a certain type of polynomial function, the quadratic, but now we're going to talk very broadly about all polynomials. So a polynomial can be defined as this right here, and I know it looks pretty intimidating with all these an x to the n power n minus 1, all that junk there. But basically, what we can summarize that to is, it's just a function that has a variable raised to some power where that power is a whole number. Your exponents must be whole numbers, and they must be positive numbers. And then the coefficients, the numbers in front, are all real numbers. So like you can't have an I in your polynomial. That would make it a non-polynomial function. In a polynomial, we have some properties. The leading coefficient is the coefficient that is paired with the highest exponent. So like when we were doing quadratic functions, we had that a value, which was always in front of x squared. That a value would be your leading coefficient. And then to write it in standard form, you want to write the polynomial in decreasing exponent order. So kind of like how when we did quadratics, I would say, let's write x squared, then x to the first power, then our constant term. That would be in standard form because we're going from the biggest exponent down to the smallest exponent. And here are just some examples of that. Like I was telling you, the quadratic function right here, when we wrote it in standard form, we went from x squared to x to the first power to no x's at all. That would be a standard form, and that a value in front would be our leading coefficient. So we have a couple names. We have the constant one, where there's no x. Linear, you guys are used to linear, like y equals mx plus b. Quadratic, we just talked about that. Cubic functions, where your biggest exponent is a 3, and quartic, where your biggest exponent is 4. So let's go down here and look at these, these functions, and we're going to determine if it's a polynomial or not, why or why not, and then if it is a polynomial, we're going to give the degree, the type, and the leading coefficient. All right, so if we look down here, we have y equals n to the negative second power minus 3. And if n is our variable, this is not a polynomial because we have a negative exponent with a variable. So negative exponent. So we can't figure out the degree or anything like that. Now, f of x equals x squared plus 5. Yes, that is a polynomial. That is a quadratic. We don't have any of those issues that we had previously. The degree, this is a second degree polynomial because x squared is the biggest exponent. The type, well, this is a quadratic, as I said. And the leading coefficient is 1. Remember, we have that invisible 1 out in front. All right, now we have x to the fourth plus x minus 3. And this is a polynomial. And the reason it's a polynomial is that we have a whole number exponents, and we have a fourth degree function because our biggest exponent is 4. That's called a quartic. And the leading coefficient, again, is an invisible 1. Now this next one, y equals 4 to the x power. This is not a polynomial because your exponent is not a whole number. Your variable is actually your in the exponent. So exponent is not a whole number. And we don't have a degree or anything for that. y equals 9, this is a polynomial. You just have x to the 0 power, and that's okay. This is a 0-degree function, and we call that a constant. It's up here as well, a constant function. And your leading coefficient here is 0. Cut. And your leading coefficient here is 9. Now this one, you may say, well, what happens to the fraction? Remember, you could write this as 1/2 times n, which is a linear function where you have a slope of 1/2. So yes, this is a polynomial. Your degree is 1. This is linear. And your leading coefficient is 1/2. Next one, 3x squared plus 4x to the 2.5 power. That means no, because your exponent is not a whole number. So exponents is not a whole number. It doesn't matter that we have a third power and a second power. That 2.5 power means it's not a polynomial function. Then y equals 7x minus the square root of 3 plus pi times x to the third power. Pi is a real number, so we could have that as a coefficient. So this is a polynomial function, yes. And what that tells us, what that means is that our degree is 3. That's the biggest exponent. This is a cubic function. And our leading coefficient is actually pi because that is a number in front of x to the third power. That square root of 3, again, is a real number. And then finally, we have a fraction, a variable in the denominator of a fraction, so that means no. Because 3 over x can be written as 3 times x to the negative 1 power, which we know from up here we can't have. So we have a negative exponent. Now on the next page, we're going to talk about end behavior of a function. And we talked about end behavior of absolute value and quadratic and linear functions, but now we're going to talk about the relationship between the degree, leading coefficient, and how that affects your end behavior. So if your degree is odd and your leading coefficient is positive, the left side of the function, so as x approaches negative infinity, the y values also approach negative infinity. And as x approaches positive infinity, the right side also approaches positive infinity. If your degree is odd and your leading coefficient is negative, it's going to be the opposite of what we just had. So the left side is going to go up. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, f of x or y approaches negative infinity. So if you have an odd degree function, you will see that the ends go in opposite directions. And if you think about a line, y equals 3x plus 5, that is an odd degree function. You have that invisible 1 here. And we know with a line, the ends go in opposite directions. So we just apply that to all odd degree functions. Now, even degree functions, we did that with quadratics, and we saw that the ends go in the same direction. And that applies to all functions with an even degree. So if we have an even degree function with a positive leading coefficient, both sides are going to go up to positive infinity. Like when we did quadratics, y equals 3x squared minus 6, both ends would go up, and 2 is even, so that applies now to all even degree functions. If we have a degree that is even with a negative leading coefficient, then both sides are going downwards. Let's look at this example down here. Describe the end behavior of the graph by completing these statements. So we're going to look at these part A in this pair, and we're going to do the end behavior, write in standard form, and all that fun stuff. So standard form means the biggest exponent goes first, and then we go in decreasing order. We have an even degree and a negative leading coefficient. So that means as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y also approaches negative infinity. And over here on the pair, this one is already written in standard form. And it doesn't matter that we don't have an x to the first power. So 4 is even, and our degree is 4, which is even. Our leading coefficient is 2, which is positive. So that means both ends are going up. And again, this is true for all of them. Now on the next page, we have negative x to the fourth plus 3x to the third plus x squared minus 4x minus 1. Again, this was already written in standard form. We have an even degree because 4 is even, but a negative leading coefficient. So as x approaches negative infinity, y also approaches negative infinity. And as x approaches positive infinity, y again approaches negative infinity. Now with example number 5 down here, we're going to look at the graph and determine is the degree even or odd, and is the leading coefficient positive or negative. So that is something that students get mixed up with a lot. When we're looking at the degree, we don't care really what the number is right now. We look at the degree and determine is it even or odd. Leading coefficient, we don't really care what the number is. We just care is the leading coefficient positive or negative. So this one, we see the ends are going in opposite directions, which means the degree must be odd. And because the right side is going up, the leading coefficient must be positive. You can always look at the right side to see if we have a positive or negative leading coefficient. The right side going up means positive, the right side going down means negative. This one right here, both ends are going down. Both ends are going in the same direction, so that means we have an even degree, and since they're going down, we have a negative leading coefficient. This one, the ends are going in opposite directions, so that is, again, an odd degree. And since the right side goes down, we're having a negative leading coefficient. So I'm hoping that this is making some sense. Again, we're not really concerned as much as what the value is as opposed to even or odd for the degree, positive and negative for the leading coefficient, because that will tell us how this polynomial function behaves. So thank you for watching. Make sure to like the video and subscribe.